This week we're going to talk about diffraction. Today we're going to discuss the meaning of diffraction and we'll relate it to the concept of lattices, direct lattice and reciprocal lattice. Next lecture we're going to look at specific examples of diffraction patterns that emerge from crystals of different kinds. All right. So I would like to begin with a few questions. First of all, what is the reciprocal lattice? What does the reciprocal lattice signify? Yes, please.
It's the Fourier transform of the direct lattice, like the general lattice.
Right.
So you can work backwards to figure out what the crystal structure is.
Okay. So what is it physically? What does each point in the reciprocal lattice represent?
Vector.
Yes.
Each point in the regular lattice represents a plane.
Each point in the reciprocal lattice represents a plane.
It's the opposite.
No, each point in the direct lattice represents a point on the lattice, but each point in the reciprocal lattice stands for a plane. Correct? Each point in the reciprocal lattice is representative of a plane. Okay. So if I were to say that the reciprocal lattice is not a true lattice, the word lattice is a misnomer for the reciprocal lattice. Why is this statement true or false?
Every point is distinct, not the same.
Exactly. Every point is distinct because every point represents a different plane. And all the planes are, of course, different. Okay, so the reciprocal lattice is not a lattice in the true sense of the word. It's just a grid of points. But those points do not form a true lattice because by definition, in a true lattice, every point is indistinguishable from the other. But the reciprocal lattice is a very convenient mathematical and an almost physical construct because it helps in understanding diffraction. And diffraction is our primary and probably the only mechanism by which we can tell what the crystal structure is. Okay. So first of all, we do know that electromagnetic radiation behaves like a wave. It has a certain wavelength, certain momentum. And if the future size in the crystal structure is comparable to the wavelength, then diffraction will occur. So X-rays are of course electromagnetic radiation. They have wavelengths which are far less than a nanometers, less than even half a nanometers and even smaller. And how are X-rays produced? How do we get X-rays? So today we're going to spend some time on diffraction. So before I'm able to do that in lecture 7, and I haven't yet forgotten that I've also asked you to do some homework before the beginning of the class. So has anyone attempted to find out the reciprocal lattice corresponding to a face-centered cubic or a face-centered body-centered cube? Okay, so have you done so? No one gets extra marks. So I had pledged to myself that anyone who did this would get extra marks in the midterm. So we're all saved. And that's why I put this in a homework problem as well. So today let's talk about the meaning of diffraction. And I think any serious physicist should really know about all of this. First of all, how are X-rays produced? What's the best way to produce X-rays? Come on.
कैथोड से कैथोड से
क्या मतलब कैथोड से? बाउंसिंग इलेक्ट्रॉन्स. उनको क्या करते हैं?
I think you just
स्ट्रक्चरली ये एटॉमिक फिजिक्स से या एटॉमिक स्ट्रक्चर से कैसे एक्सरेज आती हैं? हैं?
L, M, N से हम जब एक्साइट करते हैं तो डिफरेंट
ठीक है, तो एक्साइट शुरू में कैसे करते हैं, एनर्जी कैसे देते हैं?
Shining a light.
For example, there are different ways of excitation. So if you have a heavy atom, say, so this is the nucleus, we have a K shell, L shell, M shell. So this is our nucleus, we have electrons. Somehow we have an electron in the K shell and we excite it. Okay, which means that we ionize this K electron by some kind of incident energy. That incident energy could be in the form of electrons. So you produce electrons in a vacuum tube. Those electrons fall on a target, on an anode, and the anode is made up of a certain material. Say this material is copper. So electrons fall onto a target. You have a vacuum tube. Electrons are ejected by thermionic emission. For example, you have a cathode and an anode. The cathode, of course, is negatively charged. The anode is positively charged, and this is really a high voltage. High voltage. Electrons are ejected by thermionic emission and they fall onto this anode. So the electrons are coming in and they eject this electron. This electron is ejected and it really forms a current through this external circuit. And when the electron is ejected, there is a vacancy here in the K shell. Some higher electron in a higher shell falls down to fill up this vacancy. So for example, electron from an L shell can fall into this vacancy, and when it does so, it emits electromagnetic radiation. Since this is a big atom and this is an inner shell which is being filled, the electrons have knocked off an electron from an inner shell, not from a valence shell. So a vacancy has been created in the inner shell. Higher excited electrons, some higher state, fall down and they emit radiation. Okay, this radiation is X-ray. Since it falls down into the K shell, this radiation has a certain wavelength which depends upon the atomic number of this material and this shell. So since it falls into the K shell and fills into the K shell and it comes from a neighboring shell, the L shell, so this radiation is called K alpha X-rays. If it falls from the L shell, if this vacancy is filled from the M shell, then the radiation of course will have a shorter wavelength and a higher energy. This is called the K beta shell. So X-rays are emitted. Right? So this is how X-rays are produced. Now these X-rays, when emitted, the entire assembly is called an X-ray gun. When these X-rays are emitted, they are made to shine on our crystal, which has all the different planes that we've mentioned. And then these X-rays scatter off in different orientations, different directions. This is what we're going to explore today. So this is how X-rays are produced. So X-rays have a certain wavelength. For example, if you talk about copper, the copper K alpha radiation is about 0.154 nanometers. Okay. These electrons are ejected by thermionic emission, but there are other ways of ejecting electrons as well. Field emission is one example. Field emission means you apply such a strong electric field that electrons are stripped out of the metal. That's called a field emission source of electrons. Okay? And that's the kind of the electron microscope that we have in our laboratory downstairs. Electrons are coming out from an electron gun through field emission. Okay? If you want higher energies, then generally you would like to use materials in the anode with a higher atomic number, like molybdenum, lanthanum. For example, if I were to use molybdenum, the K alpha peak could be as small as 0.003 nanometers, which is about 3 picometers. So this is such a short wavelength, such high energy X-rays, that it has other unique advantages in diffraction studies, as I will mention shortly. So another way of probing crystal structure is through electrons themselves. Now, do electrons have a wavelength? Yes, the electrons can be accelerated. So if electrons are accelerated just by the pure application of electric fields, they will also have a wavelength, and that wavelength is given by, what's the wavelength of an electron wave? H over P. Okay, and you can also, so V naught E is the energy, half mv square. Okay, so you can also express this in terms of this momentum. This is equal to P square over 2m. So P is 2mv naught E, 2mv naught E. So if you are accelerating electrons through an electric potential V naught, this would be the wavelength of electrons. So if you have a potential of about 100 kilovolts, you put in the values, you get an extremely small wavelength, which could be even smaller than X-rays, tens to 100 times smaller than X-rays. Okay, so you can use electrons to probe crystalline structure and find out to what space group does that material belong to, what are the fractional coordinates, what planes exist, what is the crystal system, what are the lattice parameters. The lattice parameters refer to the lengths of A, B, C and to the angles alpha, beta, gamma. These are called the lattice parameters. Or that's the first time I'm using this term, lattice parameter. A, B, C, alpha, beta, gamma. Okay, so you can use X-rays or electrons.
Sir, alpha, beta, gamma
जो यूनिट सेल की जो एंगल्स हैं. Okay, so you can use X-rays in an X-ray diffraction apparatus, or you can use electrons in a transmission electron microscope setup. Okay, so these are the two basic techniques that are used for crystal structure determination. XRD, which is X-ray diffraction, and TEM, which is transmission electron microscopy. All right, I also would like to distinguish between two kinds of crystals. One are called single crystals versus polycrystalline materials. Now, in single crystals, you have certain planes, and atoms are, of course, organized on these planes. In a polycrystalline material, there are many small crystallites, which means you have, so these, for example, are the 1, 0, 0 planes, and all of them are neatly aligned with one another. All right. Now, in a polycrystalline material, you could have 1, 0, 0 planes that are oriented here, but then you can have a different region of the material in which the 1, 0, 0 planes are oriented like this, because the crystal itself in that region has rotated, physically it has rotated. Okay. And then at some later, in some other region, the 1, 0, 0 planes are oriented like this. Here they are oriented like this, 1, 0, 0. So you can have different single crystals all mixed together in distinct regions. So if I look at this from the top and I want to draw a diagram. So here is this region in which there is certain orientation of planes. Say the 1, 0, 0 planes. In this region, the orientation has changed because the crystal itself has physically rotated in that region. And then you have another region. And I'm just drawing the same planes, the 1, 0, 0 planes in all of these regions. So this one region itself is a single crystal. This region here is another single crystal itself because all the planes are perfectly aligned with one another. But then in another region, the 1, 0, 0 planes have shifted because just imagine that the entire solid has rotated. Of course, the planes will rotate with itself. So this kind of material is a polycrystalline material, which is a combination of different small single crystals. Each of these regions is also called a grain, right? So there are many grains inside this material, and there are boundaries between grains. These are called grain boundaries. Let me finish. So that when you synthesize materials, for example, you grow a crystal on a film or a substrate, and depending upon the technique of growth, you could either get polycrystalline growth or you could get single crystal growth. Single crystal growth is also called epitaxial growth. Okay? It depends upon how you are synthesizing the crystal, how you are making the material. So now if X-rays shine on this single crystal, of course there are other planes here as well. There is the, say, the 1, 1, 1 plane, but all of these planes have the fixed orientation relative to one another. Here there is a fixed orientation and then the entire structure is rotated in a different region. Rotated in a different region. In 3D. Okay, so when X-rays shine onto this material versus when X-rays shine onto this material, the behavior will be different. The diffraction pattern will come out differently. Yes, first question.
Sir, do they have different physical properties as well? Both of these, because like in my mind it's the same crystal. Like in polycrystalline lattice as well, it's just rotated differently.
Right. So if you do a study of a physical property which is orientation dependent, and if this crystal is anisotropic with respect to that property, then this crystal will show different orientational properties in the measurement of that physical property. It might, if this is a large structure and all the orientations of the crystallites are possible, then you'll just see the average. Okay? In that sense, they have the same physical properties, but the orientational dependence will be different.
I just want to confirm if one grain is, for instance, a different kind of thing, is that still a valid polycrystalline structure?
If one grain is?
If the grains are different planes, like Abhi sub 1, 0, 0.
It's still polycrystalline, but then it's not a uniform material. Right now we're just simplifying things, but this is calcium titanate, this is calcium titanate, this is calcium titanate. It's the same chemical material. Otherwise things will get very difficult, okay? So it's not a mixture in that sense. It's just a collection of different grains. Okay? And many interesting physical properties happen at the grain boundaries, by the way, including magnetic properties. These grain boundaries are kind of defects. They are also called defects, one kind of defects, because they break the very nice alignment of crystal planes. The one kind of defect. And defects harbor very important physics. Now, so this is some background. Now let's look at different formulations of diffraction. One of the easiest and something that you already know from your basic studies is the Bragg formulation for diffraction. Now the Bragg formulation is very simple. So you have a plane of atoms, some plane of atoms, and there is some spacing between the planes d. And the Bragg formulation generally works in the direct lattice picture. So you have X-rays that are coming in at a certain angle. Let's suppose the angle is theta. This is how we generally define angles in X-ray diffraction studies. It's not the angle of incidence, it's rather the angle that the X-rays make with the plane. So this is some plane spacing DHKL, and these are the HKL planes. In that, for the time being, let's assume it's a single crystal. Now what's going to happen is, if we view these planes as reflecting mirrors for X-rays, and we take a reflection oriented approach to diffraction, then these X-rays will be reflected from each plane, and depending upon whether we see an intensity here, whether we see some X-rays being emitted, they will only be emitted if these waves are in constructive mode, they are constructively interfering, and that's going to happen when the path difference, this path difference, which is 2d sine theta, is some multiple of lambda. Alright? So this is the Bragg formulation for diffraction. N is the order. Let's assume n equals 1. Let's look at the simplest order. Now this Bragg formula, as it is called, which was formulated by father and son, the two Braggs. It really is of vital importance. It's like the Newton law for diffraction. It's so simple but so powerful. And what it really does, it is connecting three quantities. It's connecting the wavelength of the X-rays, the angle theta, and the spacing between the planes. A reflection will only occur when this condition is met, when theta, d and lambda are in this very tight combination. Okay, so let me kind of give an example for this. So suppose I look at if I have some spacing between planes. So this is some plane DHKL of plane spacing, interplanar spacing DHKL, and these are HKL planes. Now suppose X-rays come in. X-rays are coming in at some angle with respect to DHKL, respect to these planes. A large part of these X-rays, of course, will pass unimpeded, unscattered, as it always happens, because there is certain cross section for scattering. But if now the angle of incidence here is, or the angle, the grazing angle is theta, the angle at which light is coming in and hitting the planes is theta. If the wavelength lambda, theta and this particular d happen to conform to this, then there will be some scattering. Now here we have viewed the scattering as a reflection process, right? So this is just a model. What's going to happen is that these X-rays, they can scatter off from these planes. So if this angle is theta, can you indicate what this angle is going to be? This angle is going to be theta as well. So this is the unscattered X-ray, correct? So let me redraw this diagram. So if I have planes, some angle theta here, some reflected ray here or scattered ray here, this angle is 2 theta, which shows the direction of the scattered ray from the unscattered direction. Okay. I'm going to prove this as well. So for the time being, let's assume that if this condition is satisfied, there is going to be a scattering process. So if X-rays are coming in, and this is the angle theta which the X-rays incident direction makes with the planes, and the spacing between the planes is DHKL, then there is going to be a scattered ray from these planes. And the scattered ray is going to come off at a certain angle, such that the deviation from the unscattered direction of these scattered rays is going to be equal to 2 theta. Okay, so this is the Bragg formulation. Now let's look at some examples, and we're going to talk more about this. First of all, there is no recourse to the reciprocal lattice at this particular point. You got this? We're just looking at the direct lattice, and there are planes in the direct lattice, and atoms can be placed on the planes, and we assume that certain planes are reflecting. When those planes reflect, it really means that the interplanar spacing d, the angle theta, and the wavelength are in a particular orientation. If this is a valid reflection, if I change the angle of incidence a little bit for the same planes, then this condition may not be satisfied. And it's possible that you do not get any scattering, do not get a scattered wave. So everything has to be fine-tuned: the angle of incidence, the interplanar spacing, and the wavelength. Once we have X-rays from our X-ray tube, we just make those X-rays monochromatic. We just let X-rays of a certain wavelength pass through so that our analysis is easier. Okay, so we keep lambda fixed. So there are so if you have, say, a copper target, you will get copper K alpha radiation, you get copper K beta radiation. They will have different wavelengths, but with the help of filters, you can make it monochromatic. Just get one radiation that you want to look at. So we have lambda that is fixed. The D's are provided by the crystal, and that's what we really want to determine, because that is the process of crystal structure determination, and from that we want to find out the lattice parameters and so on. And theta can be in our control or it cannot be in our control. If we have a single crystal, we can change the orientation of the X-ray beam or change the orientation of the crystal. Either of these processes will change the angle theta, correct? And it's possible that at some thetas there is a reflection and at others there isn't. At most locations there will not be a reflection, because it is only in this finely tuned regime that you get a reflection. However, if you had a polycrystalline material, then even if you kept the direction of the X-ray fixed wavelength, fixed direction, many thetas are available because there are many grains available. So you can get the whole spectrum, you can get all the reflections coming out from all thetas in one shot. Okay, so that's why the apparatus that is used to determine X-ray diffraction patterns from single crystals versus polycrystals or powders is different. In powders, you may not have to rotate the X-ray direction or the sample or the specimen. You may rotate it for other reasons, but that's besides the point. Okay, so now let's look at an example. So why is this theta? Because if this is theta, of course this angle is going to be theta, and this angle is theta. So this is what the Bragg formulation really means, that if this angle of incidence is theta this has to be theta. And this is also followed from the law of reflection. Because if I were to draw a normal here, then this angle must be the same as this angle. Now let's look at an example. Suppose I have a cubic primitive crystal structure, unit cell, which is primitive cubic, and I have atoms at the edges, at the vertices. And suppose this is cubic, its A is 0.5 nanometers, okay? Alright. Now for this is one homework problem, that if I have a cubic system, then there will be planes, HKL planes. If I were to take the 1, 0, 0 planes, then what is the spacing between these planes? What is D1, 0, 0? B तो नहीं है, A ही है ना, cubic है ना ये, क्या होगी D? What is the spacing between these planes? Family of equivalent planes, what's the spacing between them? बोलो सेम क्या मतलब? हाफ ही होगी ना, A होगी ना, this will be equal to A. So what will be the spacing between D2, 0, 0 planes? A over 2. Yes. So this is the 1, 0, 0 planes are this plane and this plane, right? These are the planes. So the spacing is from here to here, which is just equal to A. And the 2, 0, 0 planes are these planes and these planes in the middle, right? So the spacing is A by 2. Likewise, you can have arbitrary any planes that you wish with any HKL indices, right? And you can find out the spacing between these planes. In cubic, tetragonal and orthogonal, there are precise formulas for this. Okay, and I'll probably give this as a homework. Please note this down. So for the cubic system, the DHKL is really simple. It's A over H bar square plus K square plus L square under root, right? This simply is the interplanar spacing for the cubic unit cell. Got it? So now let's, if I were to make some planes, HKL planes, and I find out the distances between these planes. So 1, 0, 0 planes, the distance of course is A, as we've seen. Correct? So I'm just going to make a table for D over A. Okay. If I were to take, say, some other plane, 0, 2, 0. So what will be D in this case? So what's the separation between? It's going to be A over 2 or half. Okay. If I were to take, say, another plane, 2, 2, 1. Four plus 1, 9, and root 9, 3. 1 over 3. So as the Miller indices go up, the spacing between those particular planes keeps on decreasing. That's obvious. That's how we defined our Miller indices for the planes. Let's look at another example. Solar. 4. Right, so this will be 1/4. Correct? Jeez. 4, 3, 16, 9, 25. छत्तीस कैसे आएगा? 4, 4, 4, 4, 16, 16, 32, 4, 4, 2. Say 2, 4, 2, right? कुछ भी हो सकता है. 2, 4, 4. 2, 4, 4. All right. So and so on. So as the spacing gets smaller and smaller for planes with higher Miller indices. Okay, now we're going to look at the Bragg formula and what implications does this have. So the Bragg formula is really that I would like, let's take n equals 1 and let's do 2D over A. This is 2, 1, 2 by 3, 1 by 2, 2 by 5, 1 by 3. Let's take the inverse of this, A over 2D. A over 2D is 1/2, 1, 3 by 2, 2, 5 by 2, 3, and so on, right? Now what we would like to do is, suppose my A is 1/2 nanometers. 1/2 nanometers. So this is of course unitless. So for this particular unit cell, if A is 1/2 nanometer, which is a reasonable size for a unit cell, 0.5 nanometers or 5 angstroms, then I put A equals 1/2 here. So this will become, so I need to divide, actually I need to multiply this further by 2 to get 1 over 2D. In nanometer. I need to divide this by A. A is 1/2, so I multiply by 2. This is 1, 2, 3, 4, 5, 6. Okay. So this is my 1 over 2D. ठीक है?
1 over 2.
मैंने इस चीज़ को A से डिवाइड कर दिया. I'm finding out 1 over 2D. A over 2D तक आ गया ना. अब मैंने इसको 1 over 2D लेना है, मैं इस चीज़ को A से डिवाइड कर दूंगा ना. A है 1/2, तो 1 over 2D आ गया. अब now what I would like to do, I would like to look at this formula. I know that sin theta is lambda over 2D. My sin theta is lambda over 2D. Therefore my theta at which a reflection would occur for a particular plane. So if I write down the planes here again, this is 1, 0, 0 plane, 0, 2, 0 plane, 2, 2, 1 plane, 4, 0, 0 plane, 4, 3, 0 plane, and the 2, 4, 2 plane.
Inverse of lambda.
So this is sine inverse of lambda. So here I would need to calculate sine inverse of lambda into this, right? So sine inverse of lambda sine inverse of 2 lambda, sine inverse of 3 lambda, and lambda is stated now in nanometers, says in the same units as we have 1 over 2d. 1 over 2d is in per nanometer, so lambda must be in nanometers. Okay, so sine inverse of 4 lambda, sine inverse of 5 lambda, sine inverse of 6 lambda. Okay, so if my lambda is from the copper K alpha, this is 0.154 nanometers. So if I take sine inverse of 0.154, can you indicate what this theta is going to be in degrees? Can anyone fill up this table for me, please?
minus 9 होता है ना नैनोमीटर
9 को छोड़ो 0.154 लिख रहे हैं, नैनोमीटर में हमने
अच्छा नैनोमीटर पे ही रहना तो 8.86
so 8.9 degrees. इधर बताएं
17.9 27.5 38.0
आगे नहीं होगा.
और 50.4
50.4
और 67.5
4 नहीं तो एक हमने क्या करता, ये जो है 430 2/5 आ रहा है, 16 जमा 9 25 244 है, सॉरी. All right. Now what does this tell? Let me draw a diagram that shows what's going on over here. Let's consider the 100 plane. X-rays come in, and if they come in at an angle of 8.9 degrees, they will be scattered. So planes, the 100 planes in this material, which have a spacing of d over a is 1, which have a spacing of 0.5 nanometers, if there are planes inside this material at which atoms exist, then reflection will occur at 8.9 degrees. What this means is that X-rays are coming in at 8.9 degrees. This is 8.9 degrees, 9 degrees, and they will be scattered like this, okay? But this angle is 2 times 8, 2 times 9, which is about 2 times 9 is 18 degrees. So this is how X-rays will be scattered. They will be scattered at small angles. Okay. If you put X-rays at any other angle, you will not get any reflection. You will not get any scattering unless you hit a higher order with n equals 2. So only for this combination of this incident angle theta, which is 8.9 degrees, these planes will act as scattering planes, and you will get a scattered radiation in a particular orientation. This is only we're talking about 100 plane. However, if there are other planes at which atoms exist, which become scattering centers, consider the 020 plane. The 020 plane is parallel to this, but has half the spacing, right? So half the spacing as these, right? D is half. So this spacing is 0.25 nanometers here. Yes, please. ये इंटरप्लेनर स्पेसिंग है,
ए जो है वो 1/2 नैनोमीटर था, तो ये स्पेसिंग फिर उसके बराबर होगी
क्योंकि 100 प्लेन में स्पेसिंग बराबर
मतलब यहाँ पे ए और डी मैच हो रहा है,
मैच हो रहा है ना,
अदरवाइज
अदरवाइज इस केस में नहीं होगा। यहाँ पे जो d है वो 0.25 है, सो दीज आर द 2 0 प्लेन्स। नाउ वी वांट टू सी एट व्हाट एंगल डू दीज प्लेन्स स्कैटर। द एंगल इज 17.9 or 18 degrees. So when X rays come in at an angle of 18 degrees, this angle is 18 degrees. Only then would they be reflected or scattered. And the scattering direction is about 36 degrees, so roughly here. Okay, so the direction, the deviation from the unscattered is about 36 degrees. So tighter planes will give you bigger angles of scattering. If incident radiation were at any other angle, these planes would not reflect, they would be silent to the X-rays, they will be unscattering planes. Yes please.
स्कैटरिंग के लिए एंगल्स
इस फार्मूले से, ब्रैग फार्मूला से, ठीक है। Let's look at one more example. Let's look at 430. So the 430 planes will look something like this. Okay, these are the 430 planes. Now the angle is 50.4 degrees. The reflection angle is 50.4 degrees. Scattering will happen only when this condition is satisfied. So X-rays come in at, if the X-rays come in at 50.4 degrees, they will be scattered by around 100.8 degrees. Okay, so this is how the Bragg formulation works. Everything is really nice. ठीक है, so this by the way is a single crystal. If you have a polycrystalline material and there is one angle of incidence, then it's possible that there are some planes, polycrystalline material, you have all kinds of planes. Okay, and you will get, so if you put these planes onto this orientation of X-rays, right, will you get scattering or not? You will not get scattering. Okay, if you put these planes and it sees this angle of incidence, you will not get scattering. Okay, so what you would need to do is you know different angles of incidence and so on. So let me now kind of see any questions about this. एक मिनट, Let me just finish an argument. Suppose I have a small tube in which I fill in a powder of a crystalline material, and different plane orientations exist. So it's a polycrystalline material, so there are different plane orientations. There are all kinds of planes. So X-rays are coming in. Large part of them pass unscattered. Now it's possible that there is one set of planes, could be any set of planes, any HKL set of planes, for whom the Bragg condition is satisfied. Since there are many orientations possible, and all of these are grains that I've shown, there are many orientations possible for all kinds of planes. It's possible that this is condition hits bingo for one particular plane set and this particular angle of incidence. So the lambda is fixed, so you get the right combination of the angle of incidence and a particular set of planes. And some, in that case, you will get a scattered beam which is at an angle 2 theta. Okay, for some set of planes. Because there are different planes, different orientations are possible because it's polycrystalline. It's possible, right? It's possible that in a different grain, in a different region, where there is a different orientation of planes, you come across a set of planes with a particular HKL index for which this condition is satisfied. Because all of these planes satisfy the Bragg condition for different angles. And depending upon the orientation of the crystallite itself, some crystallites will be exposed in which the planes have the correct orientation. So you might get scattering at some other angle, right? Some 2 theta 2, some other angle. So if you look at this from the top, what's happening is that an incident X-ray beam is coming in and you get these outgoing scattered beams at different thetas. All right, and all of this is, by the way, happening in 3 dimensions. All right, so if I were to convert this into a practical apparatus, into a practical machine that can look at the directions of these scattered X-rays, so what would that look like? So one possibility is I have a film, some kind of film that is sensitive to X-ray, and I wrap it around the specimen. So I can have, suppose I put a film like this in 3D. So what's really happening is that if this is my sample, I am getting cones of scattered radiation. Large angles, small angles, and so on. Correct? So these are the cones, some theta here, 2 theta here, some 2 theta here. For some planes, this is a scattered direction. For some planes, this becomes a scattered direction. Correct? And it's all happening in 3D. Now, if I put some kind of photographic film around this, what would I get? So let me first try to draw this photographic film and show the orientation in some manner possible. So So here I have a capillary in which I have loaded my material, polycrystalline material, some powder, and X-rays are coming in from some entrance iris, some entrance pupil, and they be scattered. Different directions, right? And there's going to be large big spot here. It's going to be a ring here. Let me draw the rings with blue. Some ring here, some ring here, some ring here, right? And if I unwrap this photographic film and lay it out bare, like this, I wrap it up or unwrap it rather, then corresponding to this exit pupil, I will get a bright spot here that defines my theta equals 0. This will be theta equals 0 degrees. Correct? And I will get some ring here corresponding to theta 1, this one. And from this distance, if I know the kind of circumference of this film, I can tell what this, from measuring this distance with the meter rule, I can tell what the angle theta 1 is. Right? So I will get some theta 2. Some theta 3. I get all kinds of rings on the other side as well here. So these rings correspond to this side, which have two thetas greater than 90 degrees, and some entrance pupil as well. So this is like a camera, and this is a photographic film. In the old times, before we had better detectors for X-rays, now they use scintillators, sodium iodide scintillators that kind of give electronic pulses when X-rays impinge on them. But before that, one used these photographic films. But this, it's nice to demonstrate this because this actually shows the geometry of X-ray diffraction, how things are happening. So by measuring these angles, thetas, at which reflection occurs, since you know the lambda already, you know the wavelength of the X-rays, you can infer what D's are going to be. And then from looking at all the data, you can tell whether it's cubic, tetragonal, and if you find out D, if you know per hand, it's say, so you know per se it's cubic, then you can associate a plane HKL with each one of these diffraction rings. And of course you can tell the lattice spacing A from this as well, if you know. So I'll show you some examples of this in our next class. So any questions about this Bragg formulation of diffraction? You had a question? Ji.
So you have two scenarios, right? Like for example, one plane meets the same plane or it meets a different plane. So like
दोबारा बोलो.
like there are two instances in the polycrystalline structure that will happen, right? You have the same, like for example, you have 1 0 0, and then it encounters 1 0 0 again, or it encounters a different plane, right? So how does the difference in your planes lead to like your magnetic properties at the grid spacing?
Lead to magnetic properties.
Yeah, you said that there's like some sort of like difference in properties.
So what I said is that in crystals, you can have different kinds of properties in different directions. So you move along this direction, you have one elastic modulus. You move in this direction in a crystal, you have another elastic modulus. It's possible. So when you have a polycrystalline material and you are finding out the some physical property of that bulk material, and if it's anisotropic, the anisotropy may get averaged out. Okay, because all crystallites are available, all directions are possible, and when you're measuring something bulk, you get the average. Okay. So far so good for the Bragg formulation. Yes, please.
To get all the answer planes, we need to rotate the state,
So in a polycrystalline material, it's generally, it happens that all grains, many grains are there, and all the planes that have atoms show some kind of reflection. Okay, so if this material, say, is of the order of millimeter big, and your lattice spacing is of the order of nanometers, so this is 12 orders of magnitude. So large amount of material is present. Crystallite size of the order of nanometers. So all kinds of orientations invariably exist. If you have a single crystal, then it's possible that only one of the lines shows up, and then you will have to rotate the single crystal or rotate the X-rays. But in a polycrystalline or a powder material, this orientational averaging, as it is called, is there for you naturally. So now let's look at another formulation. So all of this can get really complicated if we have different crystallite directions, different grains, and different kinds of planes. So there is another formulation that also highlights the significance of the Bragg formulation, which is squarely inside the direct lattice domain. We have not yet resorted by any means to the reciprocal lattice so far. But now let's look at another construction or narrative that exposes the value of the reciprocal lattice itself. And this construction is due to another crystallographer, Ewald. Okay, so we're looking at the Ewald construction. So suppose I have a direct lattice. Of course, there are lattice points, and I'm keeping things really simple for purposes of explanation. There is an A lattice vector and there is a B lattice vector, and there is some, say, spacing between lattice points. Suppose it's cubic, so I keep that A. I can also make any other lattice I wish, but I'm just trying to keep things simple for the time being. So now if I were to draw the reciprocal lattice corresponding to this direct lattice, now this is physical space. This crystal, talking about a single crystal at the moment, this single crystal is in a certain orientation, so the planes have a certain orientation, a fixed orientation. So the reciprocal lattice derives from the direct lattice. So if I were to tilt this crystal, the reciprocal lattice will tilt with it as well. Correct? So this is 2D. So if I were to draw the reciprocal lattice corresponding to this direct lattice, on the left this is the direct lattice. Now I'm going to draw the reciprocal lattice. It's cubic, so the reciprocal lattice will also be cubic. कोशिश करता हूँ अच्छा बन जाए. Right? So this is reciprocal lattice vector A star. This is direction of reciprocal lattice B star, and each of these points corresponds to a plane. And this spacing, by the way, is now 1 over A, or 2 pi over A, sorry. Correct? And so is this. G. सेम है. क्यूबिक में बात कर रहा हूँ ना, वरना डिफरेंट भी हो सकते थे, लेकिन मैं भी सिंपल. अच्छा, नाउ एक्स रेज कम इन. सपोज एक्स रेज आर कमिंग into the direct space. They are seeing the crystal at a certain orientation. Okay, suppose this is the orientation of X rays. कोई orientation होगी X rays की, wavelength भी हमें पता है. तो अब ये एक डायरेक्शन है ना, आई कैन मूव दिस एनीवेयर, right? So vectors are translatable. I can move this anywhere while keeping, I can draw any line parallel to this, it will still be the direction of x-rays. So what I do is I want to, this is a fixed specific direction. The reciprocal lattice is related to the direct lattice. If I were to tilt this direct lattice, if this were to be tilted, this will also be tilted, है ना? So the reciprocal lattice works in tandem with the direct lattice. If I tilt AB vectors, A star, B star vectors will also be tilted correspondingly. So everything, so this really does represent, this has directional consciousness. This reciprocal lattice has directional consciousness. So if I were to draw the X-ray onto this on the reciprocal lattice, if I were to map the X-ray direction on the reciprocal lattice, now this is the evolved construction that we're talking about. So I take this direction and just draw a line parallel to this and make it go through one point, any one point in the reciprocal lattice. So this is the X-ray direction. Now this point at which this X-ray direction intersect, this is a reciprocal point, lattice point. Let's call this the origin of the reciprocal lattice point, 0, 0, 0. Okay. Now what is this point? What is the index of this point in the reciprocal space? 0, 1, 0. Because this is the B direction. This is 0, 2, 0. 0, 3, 0. This is 1, 0, 0. 1, 1, 0. 1, 2, 0. And all of these are planes really, right? This is 0, 1 bar, 0, 0, 2 bar, 0. This will be 1 bar, 1 bar, 0, and so on. So all of these are points. Now the evolved construction says that, okay, so you have your points. I draw a circle which passes through the origin, whose center of that circle is, the radius of that circle is 2 pi over lambda, inversely proportional to the wavelength, and the center lies along this line 2 pi over lambda away from this point. Okay, so let me draw a circle. Let me first draw a circle. बहुत बुरा सर्कल बना है यार. So what I could do, I could first draw this line, then draw a circle at some point, and then move the reciprocal lattice such that one point corresponds with the exit point. That's the better way of looking at it. I draw this X-ray line, I draw a circle of radius 2 pi over lambda, then take the reciprocal lattice and kind of move it around so that one of the points coincides with the exit point of the circle. Correct? I'll get the same thing. Now look at this construction. This is called the evolved circle. In fact, this exists in 3D. So the evolved sphere. It exists in 3D, though I can't draw it at the moment. Now this point is the origin O. There is some center of this circle C. This distance here is 2 pi over lambda. Now the evolved construction says, what we would like to see, which planes give a reflection. In other words, for what planes is the Bragg condition satisfied? So what we see is, of course this 0, 0, 0 is not a plane, it's just the origin of the reciprocal space. We see whether this circle intersects with any of the reciprocal lattice points. So it intersects with this point. This point is 1 bar 2 0. It intersects with this point. This is 1 bar 3 0. Oh sorry, 2 bar 2 0. 2 bar 2 0. It might also intersect with other, it's intersecting here as well, even feebly, but kind of passing through this lattice point as well. So it's intersecting with 0, 1 bar 0. There could be, I need to fill all of this is a big circle, I need to fill all of this space. Right, I fill all of this space. There is another intersection, say over here. This is 2 bar 1 2 3 4 4 bar 0. So I look at wherever there is an intersection between the evolved circle or evolved sphere and a reciprocal lattice point, there will be a reflection from that plane. All right, and you can find out, so if this is a reflection here, the crystal in the evolved construction is placed at the origin C. This is going to be a reflected ray of axis. This angle 2 theta is the direction of the scattered ray. The scattering plane is 1 bar 2 0. This will be a scattered direction as well. This will be the scattered angle 2 theta and the scattering plane will be 2 bar 2 0. Here there is going to be a scattered ray as well. The angle is this one and this is the scattering plane. So we can identify all the scattering planes and the scattered angles. When we know 2 theta, we know theta as well. So this is one mechanism by which, and this is actually equivalent to the Bragg formulation. How? This is a scattering plane. Now if I look at this triangle here, यहाँ तक बात समझ आ गई. I'm just now going to show why this is equivalent to the Bragg formulation. Any questions? So this is scattering direction, scattered direction. This is an incident direction. I draw a triangle. I bisect this side. This angle is theta. And so is this. Hmm?
220 के 2 थीटा से चल जाएगा.
नहीं, ये पूरा एंगल 2 थीटा है ना, तो बाइसेक्टर में ये थीटा है. All right. Now what is the distance of, first of all, what is this length? This length or this length? Let's say F. What is CO and CF? It's 2 pi over lambda. What is this? This is 2 pi over lambda sine theta. So OF is 2 times 2 pi over lambda sine theta. Correct? Now what is the distance of this point F? This is a plane and this is a reciprocal lattice vector. OF is actually a reciprocal lattice vector, isn't it? OF is actually a reciprocal lattice vector. Let's call it G. So this has some, say, H A star plus K B star plus L C star, right? So what is this? If this is for a cubic cell, what will be the distance of this point? It's going to be the inverse of the interplanar spacing corresponding to the HKL planes. It's going to be 2 pi over d HKL, correct? In the reciprocal space, the points are separated by 2 pi over d for the cubic construction, just for the cubic, correct? So which really means that OF is equal to 2 times 2 pi over lambda sine theta 2 pi over d. I'm just suppressing the HKL symbols, which really means the Bragg law. 2d sine theta is lambda, which is the Bragg's law. So the evolved construction, however, has some other really nice interpretations. First of all, first question. Now, in this this corresponds to a particular geometry. It corresponds to a particular direction of X-rays and a particular orientation of the real crystal. The reciprocal lattice orientation follows from it. If I were to, some planes are reflecting, others are not, and it's a single crystal. If I were to reorient this crystal, what does reorientation mean? Reorientation means the reciprocal lattice will be reoriented. So if I turn this anti-clockwise, तो ये भी anti-clockwise हो जाएगा ना? तो होगा क्या कि a reflecting plane may no longer be reflecting, because if I keep this the pivot of the reciprocal lattice and I shift everything, so let me try to draw this.
So I'm getting to a pivot period while the X-ray stays in the same direction.
X-rays are in the same direction. So suppose this is my pivot and this is the direction of X-rays. Now I rotate the crystal and my circle was somewhere like this, right? बना देता हूँ, चोरी छुपे यार बनाते इससे गुजर है. This is my initial construction. So there is an intersection here and probably somewhere else as well. And the intersection here, probably here. Okay, so there are these intersections, reflecting planes. Now what I would like to do, I'm changing the orientation of the crystal. So one way to look at it is that you rotate the entire reciprocal lattice. anti-clockwise, because you're rotating this. So when this entire grid, if I keep this as my pivot or the fulcrum, keep this unchanged, this entire thing will rotate, right? The wavelength isn't changing. थोड़ा सा complicated figure बन रही है, लेकिन now we'll get new points of intersection. Some of the old reflecting planes will now be silent, and new planes will be created, say here, here. So I can expose new planes. Another way to do exactly the same geometrical construction is to keep the reciprocal lattice fixed and rotate the x-ray direction, keeping this point as still the fulcrum to keep our lives simpler. Okay, it's also possible if you were to change the wavelength of the x-ray beam. If the wavelength were shorter, then the radius of the circle will become bigger. So if the wavelength is really big, so if you use electrons instead of X-rays, where the wavelength could be 40, 50, 60 times shorter, of the order of picometers, then this evolved sphere will become really, really large. Its radius of curvature is going to be very large. Could be order of the meter, could be of the order of meters as well, so large. Correct? In that case, the evolved sphere will be a sphere with a very large radius of curvature. And in that case, all of the points on this row of the reciprocal lattice will become reflecting. So if you shine, if you have, but the problem with there's one problem with the X-rays as compared with electrons as compared with X-rays. So if you want to do a scattering study from X-rays versus electrons, could you think of some major differences? See, what kind of size of specimen can you probe? Physically, atomistically, how are X-rays scattering? Why do X-rays scatter from an atom? Photons के through. X-ray के तो photons हैं आगे. देखो ना, एक तो Compton effect होता है. So physically, how are X-rays scattering from an atom? X-rays are electromagnetic radiation. They have an electric field. The electron cloud, its shape and its size of the electron cloud associated with the atom is giving electrostatic interaction with the X-rays, which is causing it to scatter. Right? Electrons, but X-rays are uncharged particles. Electrons have charge. So electrons, when you shine electrons on a specimen, since they are charged particles, they are more prone to absorption. Therefore, electrons cannot penetrate deeper into the material. X-rays can, because they are neutral, they are uncharged. So that's why if you want to do diffraction studies with electrons in an electron microscope, transmission electron, you need very thin specimens of the order of few atoms layer thick, like 1D, 2D, or a few layers, bilayer, trilayer. Very thin specimens are required of the order of nanometers. So if you have a specimen of this kind and you shine an electron beam onto this, an energetic electron beam onto this, there will be certain scattering directions. Certain thetas will be allowed, right? Just according to the evolved construction. And by the way, these angles are really, really small. These angles are small because the radius of curvature for electrons is very large. So any scattered beam is along this row of points in the reciprocal space. So thetas are going to be really, really small. So if you have a photographic plate here, there will be points that will accumulate on this plate, and you will get a pattern of this kind. For electrons, you get this electron diffraction pattern, which is exactly a signature of the reciprocal space itself. You can see the electron reciprocal space in electron microscopy. You can see the direct lattice. Everyone can see the direct lattice, of course, but you can also see the reciprocal lattice by using electrons which are very energetic. Okay, homework number 2 has been uploaded. Please complete the homework.